Okay, then question 1 of this paper, variables x and y are such that when log y is plotted against the square root of x, a straight line passing through these points is obtained. We want to show that y equals a times b to the power of root x, where a and b are constants to be found. Well, I think it's probably easier to work backwards. We're going to start with this thing here. So we're going to start with y equals a times by b to the power of root x, and we're going to log both sides, okay? So we're going to get here log y is equal to log of a times by b to the power of root x. Okay, now the key thing here really is understanding the log rules, okay? So let's state one of the log rules. If I've got log a plus log b, that's equal to log of a times by b. Okay, so what I can do is actually I can use that log rule here. I can split up this logarithm. So what I'm going to get is log a plus log b the square root of x. Now I can use another log rule, and this log rule is if I've got log of a to the power of p, then that is the same thing as p times by log a. So what does that mean? It means I can take this power here, the square root of x, I can bring it down to the front. So let's do that. I'm going to get log a plus the square root of x times by log b is equal to log y. Now, this thing here is actually a straight line equation, okay? But it's not so obvious at the moment. So what I'm going to do is just going to rewrite that to make it a little bit clearer. If I've got log y is equal to log b times by the square root of x plus log a. And what I want you to see here is that this is actually a y equals mx plus c graph. This is y equals mx plus c graph, right? So I've got these new variables, big Y and big X. Well, big Y is the same as log Y. Big X is the same thing as the square root of X. So our gradient here will be equal to log B, and our y-intercept C is going to be the same as log A, right? And this makes sense because the question tells us if we plot log Y against the square root of X, and that is exactly what we've got, right? We've got log Y plotted against the square root of X. Okay, now then, what do we want to find then? We basically want to find the gradient of this graph. We want to find the y-intercept. Well, how are we going to find the gradient? Well, we can find the gradient by looking at this thing here. We take the gradient between these 2 points. So the gradient is y2 is 8 minus y1, which is 5. Y2 minus y1 over x2, 2.5, minus x1, which is 1. Okay, so we're going to do that. So the gradient m is y2 minus y1 over x2 minus x1. And that's going to be equal, as I said, to 8 minus 5 over 2.5 minus 1. 8 minus 5 over 2.5 minus 1. 8 minus 5 is 3. And 2.5 minus 1 is 1.5, which is the same as 3 upon 2. So 3 divided by 3 upon 2 is just 2. So our gradient is 2. Now, why is that helpful? Well, because we just said a moment ago that our gradient is the same thing as log b. So if that's the case, then what we're able to say is therefore log b is equal to 2. And therefore b must be equal to 10 to the power of 2. And 10 to the power of 2 is the same thing as 100. Okay, so we can actually now rewrite our equation, y equals mx plus c. We can say, actually, this is now y is equal to 2x plus c. Okay, 2x plus c. All right, then we can now substitute one of the points into this equation to find out what c is. So let's take our point. Let's take the point 1, 5. Okay, when y is equal to 5, x is equal to 1. So 5 is equal to 2 times by 1 plus c. And that means that c is equal to 3. And of course, what we said earlier is that our c is the same thing as log a. Right? So log a is equal to c. Okay, so log a is equal to c. So therefore log a is equal to 3. And that means that a is equal to 10 to the power of 3. Okay, or the same thing as 1,000. Okay. So then, if that's the case, well, we can just substitute these values back into our expression here, right? This thing here. So A is 1,000, B is 100. So therefore, our final answer is going to be y is equal to 10 to the 3, 1,000, times by b, which is 100, to the power of root x. Okay, and that's our answer to question 1. Okay, so this is question 2. We've got to sketch a trigonometric graph. Now what I'm going to do is I'm just going to rewrite this graph as 4 cos 6x plus 2, because that's probably the way most of you are familiar with it. And really the key to sketching this is to understand what these numbers here mean, which I will call A, B, and C. And I suggest that what you do is actually you work in reverse order. So I'm going to start with the last number here. What does that refer to? That is the shift in the y direction, so the shift in y. So the whole graph, the center line moves up to y is equal to 2. I'm just going to put that on there. So the center line for our curve is going to be y is equal to 2. Okay, then what does this number here refer to, the 6? Well, that tells us the number of waves in 360 degrees. Okay, it's what we call the circular frequency. Okay, what this means is that there are 6 waves in 360 degrees. Now, if there are 6 waves in 360 degrees, one wave will be 360 divided by 6. It's what we call the period of the wave. 360 degrees divided by 6. And so that will be equal to 60 degrees. So in other words, each single wave takes up 60 degrees. All right, then lastly, what's this for? This for is the amplitude. The amplitude is how much above the center line the curve will go and how much below it will go. So if we're going to be going up by 4, like that, then the peak value will be 2 plus 4, which is 6, right? So the graph is going to be going all the way up to positive 6. And it will also be coming down from 2 to negative 2 there, like that. We know that our graph is going to be between these lines. It's a cosine graph. Now, the cosine graph means it's going to start here, right? And we know that one period is 60 degrees, so it's going to start there and it's going to end here at 60 degrees. So what will our wave look like? I'm going to do something like this. I know this is not going to be great, guys. I'm sorry about sketching it on a tablet. It'll be something like that. Okay, so that's half a wave up to here. Ooh. Is going to be a full wave, and down to here. Ooh. That. Like that. Okay, so that should be what our graph looks like. This is a cosine, right? It's a cosine because it starts here. It's got a center line at 2, got an amplitude of 4, it goes up and down by 4, and it's got a period of 60 degrees because that's 360 divided by 6. Okay, and now we've got to look at parts B and C of this question. Well, what does part B say? Part B asks us to state the amplitude. Well, we've already done that. The amplitude is 4. And it asks us to state the period of G. Well, we've already done that. That is 60 degrees. Okay, guys, here we are in question 3. We have got a cubic polynomial here. And we're told that the polynomial can be expressed in this form, x plus a squared, bracket b plus cx. We want to find a, b, and c. Now, this x plus a squared, what does that mean? Well, it means that that represents a repeated root, right? A root which happens twice on the same point. Now, where is that? Well, it's going to be where the curve touches the x-axis, right? So if every time you've got a curve that touches the x-axis, then that is a repeated root, okay? Repeated root. So that repeated root is where x is equal to negative 2. Right, so we can write that down. So x is equal to negative 2 is a root. And we can rearrange that to be x plus 2 equals 0. So x plus 2 equals 0 is the factor, or rather x plus 2 is the factor. But we've got 2 of these. And so we can say the factor will be x plus 2 squared because that's the repeated root. Okay, now let's have a look at the next root. We just scroll down. We can see the other root is here, where x is equal to 1.5 or 3 upon 2. I'll write that down now. So x is equal to 3 upon 2. If I was to rearrange that, we get x minus 3 upon 2 equals 0. And if we multiply both sides by 2, we're going to get 2x minus 3 equals 0. And so we could say that 2x minus 3 is going to be our factor. So we've got factors here of x plus 2, and we've got x plus 2 twice, x plus 2 squared, and we've got another factor of 2x minus 3. Now, there's a subtlety to this question. The subtlety is that the cubic here is a negative cubic, right? It's a cubic that's kind of sloping down. Now, if you're not sure about that, a positive cubic who's got a positive x cubed term is going to be sloping up like that. The negative cubic, negative x cubed term, is going to be going down like that. Well, we've got a negative cubic in this case. That means that if we were to multiply everything out, we should get is a negative x cubed expression. So what we could say is, okay, our polynomial is going to look like the following. H of x is equal to x plus 2 squared, bracket 2x minus 3, but with a negative in front of it, okay, to make sure that we get our negative cubic. And what that's going to do is it means that we can rewrite this as x plus 2 squared times by 3 minus 2x. In other words, what we've done is we've taken our negative sign and we've multiplied it into here, which means we flip this to be 3 minus 2x. Now, there's also one other thing we just need to be a little bit careful about, which is we can't assume that the x cubed is going to be a 1x cubed. It could be a 2x cubed or a 3x cubed or a 4x cubed. So I'm going to put a k there because I just want to check what that value of k is. And the way we're going to do that is we're going to use the y-intercept. Again, the y-intercept is going to be 12. So what I'm going to say is when x is equal to 0, y should be equal to 12. So I'm just going to put that in. We're going to get 12 is equal to k, bracket 0 plus 2 squared, bracket 3 minus 0. And so 2 squared is 4, times by 3 is 12. We're going to get 12 is equal to 12k, which means that k is equal to 1. So I can actually say that the h of x is just x plus 2 squared, bracket 3 minus 2x. That last step there, you just need to be a little bit careful, right? Because the question could just be a tiny bit different, and it means that you could so easily ignore that last step. But it's important that you recognize that. So what is our value of a? Well, our value of a is the 2. What's our value of b? The value of b is the 3. And what's the value of c? The value of c, I think there is negative 2, isn't it? We just go back up there. Yeah, okay. So I hope that was helpful. Okay, then part B of this question, we are asked to use the graph to solve the inequality h of x is less than or equal to 9. Well, I think what we've got to do is we've got to find out where h of x is equal to 9, which is here, and we're going to draw a straight line through that. So let me just draw a straight line. I hope I get this right. Something like that-ish. It's not perfect, I'm sorry about that. So where is the curve going to be less than 9? Well, it's going to be less than 9 between here and here, and less than 9 here. Okay, so what we're really being asked to do is being asked to identify this particular region of the curve. So I'll highlight it in green, I guess. So that particular region there. And this particular region here. So what values of x give us that? Well, we just got to go down really and look at the graph. If I go down here, go down, 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 down. That looks like x is equal to negative 3. If I go down, 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 looks like x is negative a half. And if I do the same here, go down, 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 that looks like x is greater than, or x is equal to 1. So what's the region which I'm satisfying the inequality? Well, I've got to be between negative 3 and negative a half. Okay, those two values, and it will be greater than 1. Okay, so I'm just going to write that down. So x must be greater than or equal to negative 3 and a bit tidier. Negative 3 and less than or equal to negative a half. And also x must be greater than or equal to positive 1. All right, so just use the graph. Hopefully that should give you answers. Okay, here we've got question 4. Now this is a kind of question that looks very similar to the kind of the indices style questions on previous papers. But I think probably this question is easy to handle with logarithms instead. Now, the way I'm going to do this is first I'm going to state the log rules for those of you who may have forgotten. If we've got the log of a times by b, then that's equal to the log of a plus the log of b. Okay, so that's the first rule. And the second rule is if we've got the log of a divided by b, then that's going to be equal to the log of a minus the log of b. And lastly, if I've got log of a to the power of p, then that's equal to p times by the log of a. Okay, now how am I going to use that in this question? Well, I think what I'm going to do first is I'm going to log both sides. So I'm going to write this as log 5 to the power of 2y to y minus 1 is equal to log 6 times by 3 to the power of y. Okay, now I can use the third rule on this power here, right? So I'm going to take that power, I'm going to bring it down to the front using this rule here. So instead I'm going to write 2y minus 1 times by log 5. Okay, now here, because I've got log 6 times by 3 to the power of y, I can split that up using the first log rule, right? So if I've got log of a times by b, that's equal to log a plus log b. What I'm going to do here is I'm going to write this as log 6 plus log 3 to the power of y. Again, with this thing, I can use the log rule 3 and bring that power of y down to the front. So if I was to rewrite this, I get 2y minus 1 times by log 5 is equal to log 6 plus y times by log 3. Now, what I would want to do here, I think, is to bring all of the terms with y onto one side. So I'm going to expand the left-hand side. That will give me 2y times by log 5 minus log 5 is equal to log 6 plus y log 3. And I'm going to bring all the y terms onto the left-hand side, and I'm going to bring all of the non-y terms onto the right-hand side. So in other words, I'm going to take that term, I'm going to move it to the left. I'm going to take this log 5 here, I'm going to move it to the right. If I do that, I'm going to get 2y log 5 minus y log 3 is equal to log 6 plus log 5. Okay, now I'm going to factorize out the y from the left-hand side. If I do that, I'm going to get y bracket 2 log 5 minus log 3 is equal to, well, I can actually simplify the right-hand side, right? Because I've got log a plus log b is going to be equal to log a times by b. That's the first log rule. I can write that as log 30. Okay. All right, then I can also actually simplify this thing here, I think. Let's make that nice and easy. So firstly, I can take the 2, bring it up as a power of 5 using the third log rule. So that'd be log 5 to the power of 2 minus log 3. And then I can use the second log rule because I've got log a minus log b. That should be equal to log a divided by b, right? So if you're not sure, I'm going to be using this rule here. Okay, come down. And that will give me y times by log 5 squared, which is 25, over 3. And so therefore, in the end, what I should get is that y is equal to log 30 divided by log of 25 over 3. Okay, and that should be your answer. What you're going to have to do is you've just got to plug that into your calculator. And if you do that, you should get 1.604. Okay. All right. Now, I just want to highlight as well that you could have just directly plugged into your calculator at this stage here, right? You could have done log 30 divided by 2 log 5 minus log 3. That'd be absolutely fine. I just wanted to demonstrate how to simplify this, even though it is unnecessary I think it's just helpful for you to be comfortable with manipulating the logs and simplifying them as much as possible. Okay? Okay, so here we've got part B, which is going to be an indices question. We are supposed to solve this thing here, e to the 2x minus 4 plus 3e to the minus 2x is equal to 0. Now, generally speaking, I would say you want to get rid of this particular thing first in questions like this because it just makes things more complicated. And the way you're going to do that is you're going to multiply both sides of the equation by e to the 2x. Okay, so if I multiply the whole left-hand side by e to the 2x, then here I'm going to get e to the 4x minus 4e to the 2x plus 3. And if I multiply the right-hand side by e to the 2x, I just get 0 there. Okay? Now, what I hope you'll notice is that this is actually a quadratic. It's a quadratic in e to the 2x. Let me try to demonstrate why. Because the e to the 4x can be written as e to the 2x all squared. And so therefore, I think it may help you to see this by saying let u equal e to the 2x. Okay, and if we do that, then what we're going to end up with is u squared minus 4u plus 3 is equal to 0. That's very clearly a quadratic, and that's a quadratic that will factorize to give u minus 3 times by u minus 1. And so that's going to have solutions u is equal to 1 and u is equal to 3. Well, we just said that u is equal to e to the 2x. So what we're really doing is we're solving e to the 2x is equal to 1 and e to the 2x is equal to 3. We can use natural logs here. If we use natural logs for the first solution, we get 2x is equal to ln 1. And of course, ln 1 is 0. So x here will equal 0. That's one solution. On the other side, if we use the natural logs, 2x is equal to ln 3. And therefore, x will equal to a half ln 3. Sorry, I just tied it up. Otherwise, it looks like minus a half. Okay, equal to a half ln 3. Those are our two answers there. Okay, question 5 here, which is a connected rate of change style question. So we've got the volume of a sphere, which is given as 4/3 pi r cubed. And this sphere is increasing at a constant rate of 24 centimeters cubed per second. We want to find the rate of increase of the radius when the radius is equal to 6. Now, I think often the key to these kind of questions is interpreting what we've got here. So if we're told that the volume of the sphere is increasing at 24 centimeters cubed per second, then that means that dv dt is equal to 24. Now, what does dv dt mean? It means the rate of change of v, which is the volume, with respect to t, which is time, right? So this is the rate of change of volume with respect to time, and we know that's 24. Now, sometimes if you're not sure about this, the units are a real clue. We've got centimeters cubed here per second, right? So we've got volume per time. So we know we've got dv dt. What are we being asked to find? We're being asked to find the rate of increase of the radius. Now, of course, what it really means is the rate of increase of the radius with respect to time. So we want to find the r dt, okay, the rate of change of r with respect to t, when the radius is equal to 6. Okay, now then, how are we going to do this? Well, it's a connected rate of change, so we can say that dv dt must be equal to dv dr times by dr dt, right? This is a chain rule, the chain rule. We are connecting the rate of change of the volume with respect to time, which we have, well, that's 24, with the rate of change of the radius with respect to time, which is the thing that we want. The way they're connected is through this thing, dv dr. Now, if you're not sure how to get to that point, what you've got to recognize is this thing is kind of like a chain rule. Because if we were to multiply these two things together here on the right-hand side, then you should see that the drs are going to cancel off like that, right? Dr and dr. And we will be left on the right-hand side with dv dt, which is the thing that we want. So you can kind of treat these things like fractions. It's not really true, but you can imagine it that way. And what you're looking for is you want one of the variables to cancel off, in this case, the r. So you're left with the thing that you want, which is dv dt. Okay. All right, then let's just try to find out the thing that we need, which is this dv dr term here. Well, we know that the volume is equal to 4/3 pi r cubed. And so if we differentiate this with respect to the radius, so if we do dv dr, then what we will get is 4 pi r squared. Okay, so then we can just substitute this into this particular equation here. So dv dt is 24, dv dr is 4 pi r squared, and dr dt is the thing that we want. And what we're saying is we want this when r is equal to 6. So when r is equal to 6, then 24 is equal to 4 pi times by 36 times by dr dt. And so dr dt, if we just rearrange, dr dt is going to be equal to, well, 24 divided by 4, that's going to be 6 over 36 pi. And if we can cancel that down, that's going to give us 1 over 6 pi. Okay, and the units for that will be centimeters per second. Okay, so just go back up to the question. And maybe we want to calculate what this is in decimals, in which case we need to key this into our calculator. And if we do that, that gets 0.0531 to 3 significant figures. Okay, now guys, I took a little bit of time to explain that, and I'm sure some of you can do it a lot faster, but the point is I just want you to understand this principle here, right? Basically, the key thing to doing these questions, you got to understand what each of the statements means and be able to write them kind of like this, yeah? And you need to understand this principle here, right? This is a chain rule here. You got to try to write down an expression like this for these questions such that you cancel off the thing that you don't want, okay? I hope you understand that. I hope it was helpful. Okay, so here we are in question 6, which is a vectors question. We've got the position vectors of the points P, Q, and R, which are given by this, this, and this. The point R lies on PQ extended, such that 3 times the vector QR is equal to 2 times the vector PR. We want to use a vector method to find X and Y. Okay, well, I think the key to this is going to be finding a vector QR and finding a vector PR. So how can we find QR? QR is going to be the vector OR minus OQ. Okay, and what is the vector OR? Well, it's the XY. We've got XY there. And what is the vector OQ? It's the this one here, the 8, 5. So we're going to write that down, minus 8, 5. That means that this vector here is x minus 8, y minus 5. Okay, now we can do a similar thing for the vector PR. So we're going to get PR is the same thing as OR minus OP. And again, OR is the vector XY. And OP is the vector 4, 7. And so this will be x minus 4 and y minus 7. Okay, now what do we know? We know that 3 times by QR, so 3 times by this vector, is going to equal to 2 times by that vector there. So we can just substitute in. We're going to get 3 times by x minus 8, y minus 5. It's got to be equal to 2 times by x minus 4, y minus 7. Okay, so we end up with 2 equations, right? So let's take the one in x. So we've got 3 bracket x minus 8 is equal to 2 bracket x minus 4. So that's 3x minus 24 is equal to 2x minus 8. And so therefore x is equal to 16. Okay, and we can do exactly the same thing for the y. We've got 3 bracket y minus 5 is equal to 2 bracket y minus 7. So 3y minus 15 is equal to 2y minus 14. So therefore y is going to be equal to 1. Okay, and that means therefore that the vector OR is 16, 1. So OR is equal to 16, 1. All right, so we're in part B of our vectors question. We are given that I is a unit vector due east and j is a unit vector due north. And that may sound like it's a bit complicated, but really all that is saying is that I is this thing, vector going to the right, and j is this thing, the vector going up. Okay, so it's actually just the usual thing that we're familiar with. Okay, but of course in this question, j is in the direction of north and I is in the direction of east. Okay. All right, we've got three vectors A, B, and C that are on the same horizontal plane, and are such that A plus B is equal to C. The magnitude and bearing of A are 5 and 210. The magnitude and bearing of C are 10 and 330. We want to find A and C in terms of I and J. Well, the best thing to do here is really just to draw this out. So here we've got due north. Okay, so that's due north. So what's the vector A going to look like? Well, it's got a magnitude of 5 and it's at a direction of 210. So 210 degrees is going to be like something like that, where the angle that this makes with the downward vertical is going to be 30 degrees. Okay, why is that? Well, because the angle going from here all the way to there is 180, right? So from north to south is 180. If you add another 30 degrees, you're going to get 210. So what we got here is we've got a vector of magnitude 5 that makes this angle. So if we want to find its I and j components, we're asking basically what is this component here and what is this component here, right? The horizontal and vertical components. And the way we can do that is we can do some trigonometry. Let's call that x, I guess. Let's call that y. And we can say that x is going to be equal, x will be equal to 5 sine 30 degrees. And the reason for that, right, you can see is that this is the opposite side. So sine 30 is going to be x upon 5. And 30 degrees is a half. So we can just say that this is going to be 5 upon 2, or 2.5. Okay, what would our y be? Well, similar thing. The y is the adjacent side, so that will be 5 cos 30 degrees. Okay, and cos 30 degrees is root 3 upon 2, so this is going to be 5 root 3 upon 2. Now, we've just got to be a little bit careful here because what's happening is the horizontal component is going to the left and the vertical component is going down. So actually, this vector here, A, is going to be minus 5 upon 2 in the I direction. Right over there, I think, just to be clear. So A is going to be equal to minus 5 upon 2 in the I direction and minus 5 root 3 upon 2 in the j direction, right? Because it's going a little bit to the left and a little bit down, so they're both negative. Okay, we can do the same thing, I think, for C. C is on a bearing of 330. Well, 360 is going to be one full rotation, isn't it? So a bearing of 330 is just going to be 30 degrees anti-clockwise of that. So here that will be like that, where this angle here is going to be 30 degrees. Okay, and this has got a magnitude of 10. And again, what we want to do is we want to find the components that are horizontal and that are vertical. Okay, so it's that and that. Okay, well, again, why don't we call this thing x? We call that thing y. And so in this particular case, what can we say? Actually, I'll just label it ever so slightly differently just to make the triangle more clear. Okay, I'll call that thing there the x, and this thing here the y. So again, we've got a nice right angle triangle. So in this case, x is going to be equal to 10 sine 30 degrees, right? Because it is the opposite side. So opposite over hypotenuse will equal to sine 30. And sine 30 is a half, so this is 5. A similar thing for y. Y is going to be equal to 10 cosine 30 degrees because that is the adjacent side. And so we can say that cosine 30 is root 3 upon 2, so this is 5 root 3. So therefore, what's the vector b? Sorry, is it the vector b? Just make sure I get it right. It's vector c, isn't it? Beg your pardon. The vector c is what? Well, it's going to the left, isn't it? So it's going to be minus 5i, and it's going up, so it'll be plus 5 root 3j. Okay, so our answers are going to be that a is minus 5 upon 2 in the I direction, and minus 5 root 3 upon 2 in the j direction, and c is going to be minus 5i in the I direction, and plus 5 root 3 in the j direction. Okay, so here we are in the last part of our vectors question. We want to find the magnitude and bearing of B. Well, we've already calculated what A is and what C is in the previous part of the question, and we were also told that A plus B is equal to C. So B is going to be equal to the vector C minus the vector A. So we can just substitute in. So our C is the minus 5 root 3. And our A is minus 5 upon 2 minus 5 root 3 upon 2. Okay, so we're going to have minus 5 minus 5 upon 2. So that's minus 5 plus 5 upon 2. And that's the same thing as minus 5 upon 2. And we've got 5 root 3 minus 5 root 3 upon 2. Well, if we're not so sure about the how to do that there, we've got 5 root 3 plus 5 root 3 upon 2. We can convert this fraction to be 10 root 3 upon 2 plus 5 root 3 upon 2, right? So we give it the same denominator, and that therefore is going to be equal to 15 root 3 upon 2. So we can go back over here and say this is 15 root 3 upon 2. Okay, so that's actually going to be our vector. And what we want to do is we want to find the magnitude and direction of that vector. Well, probably a helpful idea is actually just to draw out what this is going to look like, right? Let's visualize this vector. We're going minus 5 upon 2 to the left because it's a negative. So let's draw that on. So we're going that way there. 5 upon 2 to the left. And we're going 15 root 3 upon 2 up. Okay, so that's 15 root 3 upon 2, like that. And so our total vector is going to be this thing here. That's going to be our vector B. Okay, so how can we find the magnitude of that vector? Well, the magnitude is basically Pythagoras, isn't it? Right? It will be the square root of 5 upon 2 squared plus 15 root 3 upon 2 squared. Let's try to go through that. What we're going to get here is the square root of 25 upon 4. Then if we square both sides there, we're going to get 225, that's 15 squared, times by 3, all upon 4. Okay? Okay, and 225 times by 3 is 675. So we can do 675 plus 25, which is 700. We're going to get the square root of 700 all upon 4. And hopefully we can recognize we can simplify this because we can write it as firstly a half times by the square root of 700. And 700 is 7 times by 100. So we can pull out 10. I'll just kind of do that slowly in case you're not sure. So this is the square root of 7 times by 100. The square root of 100 is 10. We get a half times by 10 times by the square root of 7, which is equal to 5 root 7. We end up with 5 root 7 there. Now, are we asked for the exact value? Let me just go up and check. No, it doesn't say the exact value. So maybe what we want to do is we want to just find the numerical value in our calculator. So 5 root 7, that is equal to 13.2 to 3 significant figures. Okay, so that is 13.2. All right. Now then, what we want to do is we want to find the bearing. Well, probably the easiest thing to do here is firstly to find this angle. I'll put it in red. I want to find that angle, we'll call that theta. And how are we going to do that? Well, we could say that tan theta is equal to the opposite, which is 15 root 3 upon 2, divided by the adjacent, which is 5 upon 2. Well, the halves are going to cancel off, right? So times top and bottom by 2 means that this thing here is going to go. Divide bottom by 5, which means that that thing there is going to go, become 3. So tan theta is equal to 3 root 3. Okay, so tan theta is equal to 3 root 3. So theta is going to be the tan inverse of 3 root 3. Well, let me just do that. So 3 root 3, tan inverse of that is, I think my calculator was set to radians there, which is a bit annoying. Do that one more time. So 3 root 3, the tan inverse of the answer is 79 degrees. 79.1 degrees to 3 significant figures. Now we've got to remember that what we're actually doing is we're finding the bearing, right? The bearing is going to be this whole angle here, right? So it's going to be 79 plus this angle, right? That angle there, and that angle is going to be 270, right? Because it's you're going around 3/4 of one full rotation. So the bearing is 79.1 plus 270. So bearing equal to, let me just add 270 to that, plus 270 is 349 degrees. Okay, that should be our answer, 13.2 on a bearing of 349. Okay, so here we are in the next question. This is essentially an integration question. We've got a curve y equals 6x minus x squared, and the line y equals x. We're asked to find the area of the shaded region. Now, before we do any integration, I think it's important that we just kind of take a step back, think about what the problem is asking. It's asking us to find this area here that's shaded. Well, what's a good way of thinking about that? Well, we could find the area underneath the curve. If we find the area underneath the curve, that's going to be this whole area here, right, that thing. And then we can subtract away from that the area under the line, which is this thing here in green. Okay. Now, what's actually the area in green? Well, the area in green is just the area of a triangle, isn't it? So really what we can do is we can integrate the curve between 0 and 5, and that will give us the area in yellow, the whole thing under the curve. And then we can subtract off from it the area of this triangle here in green. Now, in order to do that, what we're going to need to know is we're going to need to know this coordinate here, and actually that's quite straightforward, because if the x-coordinate is 5 and y is equal to x, then the y-coordinate there is going to be 5 as well. Okay, so that should be fairly straightforward. Okay, then, so what we need to do now is we need to find the area of each region. So we're going to find the area under the curve first. That's area 1. I'll call that, and that's equal to the integral of 6x minus x squared dx. And we're integrating between 0 and 5, right? Because that's our x-coordinate for our lower bound all the way up to the upper bound. So if we integrate that, we will get 3x squared minus x cubed upon 3. And we're going to substitute in our bounds 5 and 0. If I substitute in 5, I'm going to get 3 times by 5 squared. That's 75 minus 5 cubed, which is 125 over 3. And if we substitute in the lower bound, which is 0, we're just going to get 0 there. Okay, now let's try to simplify things a little bit, I think. Can we give this all a common denominator? Yes, I'm going to convert everything to thirds. So 75 times by 3 is going to be 225 over 3. Minus 125 over 3, and that will give us 100 over 3. Okay, so that's the area under the curve. Now let's find the area of the triangle, which I'll call area 2. Well, that's equal to a half of base times by height. Well, what's the base? The base is 5, that distance there. What's the height? The height is 5, that's that distance there. The area is going to be a half of 5 times by 5. And so that's going to be equal to 25 divided by 2. Okay then, so what's the area of the shaded region? The area of the shaded is going to be equal to the area under the curve minus the area under the triangle. And we just got to simplify this, so I'm going to turn them into fractions. We're going to get 200 upon 6 minus 75 upon 6, and that's going to be equal to 125 all upon 6. Okay? Okay, so then part B of this question, we've got 2 integrations to do. Let's just do them. Now, the first thing to do, I suggest, is to convert this thing here to indices form. So if I convert to indices form, I've got the integral of 2x minus 6 to the power of negative 3 plus cos x dx. Now, if I integrate that, then what happens is, to integrate the bracket, I increase this power by 1. That becomes negative 2. I divide by that new power, negative 2. then what I've got to do is I've got to take the coefficient of x in here, which is 2, and divide by that as well. So let me just reiterate. 2x minus 6, increase the power by 1 to negative 2. I divide by that new power, which is negative 2. And I take the coefficient of x, which is 2, and I divide by that. And that's integrated that term. And then if I integrate cos, well, sine differentiates to give cos, so cos will integrate to give sine x. Okay? And so then I've got to remember, I've also got to include the constant of integration, which is c. If I was to just rewrite this, I would get minus a quarter 2x minus 6 to the power of negative 2 plus sine x plus c. And if I suppose I want to make it look tidy, then what I could say is this is minus 1 upon 4 brackets 2x minus 6 squared plus sine x plus c. Okay, so that's the first one. Second one here, well, probably the easiest thing to do with this is to expand the bracket at the top. So we're going to be integrating x to the power of 8 plus 2x to the power of 4 plus 1, all divided through by 2x dx. So now I have to divide each of these terms through by 2x. So x to the power of 8 divided by 2x is going to be a half x to the power of 7. 2x to the power of 4 divided by x is x to the power of 3 plus a half x to the power of negative 1, right? Because really what this is, if you're not too sure, is that is 1 upon 2x. 1 upon 2x can be written as 1 upon 2 times by 1 upon x, and 1 upon x can be rewritten as x to the power of negative 1, right? That's what I've done there if you're not following, okay? All right then, so now what I've got to do is just got to integrate those terms, okay? So if I was to integrate the first, I raise the power by 1, and I divide by the new power, so I've got to divide by 8. This is going to be x to the power 8 upon 16. Second term, increase the power by 1, gives me x to the power 4, divide by the new power, like that. And this one, of course, if I integrate 1 upon x, then what I get is ln x. Actually, that probably wasn't very helpful, right? If I integrate 1 upon x dx, I get ln x there. Okay, so we've got to recognize that this thing is actually a different type of integration. Okay, so we get a half ln x plus k. Now, I suspect that a lot of students, what's going to happen is they're going to look at that and they're going to do the same thing. They're going to raise the power by 1. They're going to get x to the power of 0. They're going to divide by 0. And they're going to go, hang on, what's happening there? You got to remember, actually, if we're integrating 1 upon x, that's ln x, is a different type of integration. Okay, I hope that was helpful. Okay, so here we are in the next question. Here we've got a diagram showing the graph of f of x, where f of x is this function here for a domain between 0 and 3. And we want to find the domain and the range of the f inverse function. Now, I think it's probably helpful straight away. We want to find out what the y coordinate is here. Okay, so the y coordinate is going to be found by substituting in x is equal to 3 into our function. Okay, so we're going to do that. Okay, so when x is equal to 3, y is going to equal to 3 times by 3, which is 9, over the square root of 5 times by 3, 15 plus 1, so the square root of 16. That's going to be 9 upon 4, or 2.25. So this coordinate here is 2.25. Now then, what we want to find is we want to find the domain and range of the inverse function. Now, to understand this, really you've got to comprehend what's happening with an inverse function. So I'm going to think of it this way. Here we've got our original function, like that. And we've got our inverse function here, which is f inverse. Now, an original function, what it does, it takes in inputs, which are usually labeled x, and it gives out outputs, which we usually call y. What is the job of the inverse function? The inverse function is supposed to take those outputs and give you back the original inputs. Now, probably easier shown with an example. Let's say here x was whatever. We'll use the example here, right? If x is 3, we should get an output of 9 upon 4. So what's the inverse function going to do? It's going to take that output of 9 upon 4, and it should return us back to 3. Right? That's its job. That is what the inverse function is there to do, to take us from the output back to the original input. Now, What is domain and range? Well, domain is the set of all the input values, right? Domain is the set of all the input values. And the range is the set of all the output values. So here what we've got is we've got the domain of f. And here what we will have is we'll have the range of f. Now, what you should notice is that the outputs of the original function are going to become the inputs of the inverse function. That means that the domain of our inverse function, right, that thing should actually be the same as the range of our original function, right? These two things are one and the same. And then the range of our output function, the range of our inverse function rather, that should be the same as the domain of our original function, right? Because what we're saying is, what are all the possible inputs to the inverse function? Well, it's the same thing as the outputs to the original function. And what are all the outputs to the inverse function? Well, it should be the same as the set of all the inputs for the original function. So big idea is for an inverse function, the domain and the range switch places of that for the original function. Okay, so in other words, the domain of the inverse is the same as the range of the original, and the range of the inverse is the same as the domain of the original. So if we go to here, we look at our original function, f. The domain of f is everything between 0 and 3. So the domain is x is everything between 0 and 3. Now, what's the range of our original function? Well, it's everything between 0 and 2.25. It's that thing there. Okay? So the range is going to be everything between 0 and 2.25. Now then, for the inverse function, what's going to happen? Well, the domain of the inverse function is going to be the same as the range of the original function. It's going to be the same as that. So this is going to be x is everything between 0 and 2.25. And what's the range of the inverse function going to be? Well, it's going to be the same as the domain of the original function. So y has got to be everything between 0 and 3. In other words, these guys here, they switch places. Okay, that's the key idea. Okay then, so part 2 of this question, we want to solve when f of x is equal to x. Well, what is f of x? It's 3x over the square root of 5x plus 1. Okay, so let's do that. So 3x over the square root of 5x plus 1. Okay, and that's supposed to be equal to x. Now, I'm going to multiply both sides by the square root of 5x plus 1. So 3x is equal to x times by the square root of 5x plus 1. Now, it's very, very tempting to just divide through by x, but I encourage you not to do that because the danger is you forget that there's a solution when x is equal to 0. So instead, what I'm going to do is I'm going to bring everything on the right to the left-hand side. So we're going to get 3x minus x square root 5x plus 1 equals 0. I will then factorize out the x, so I get x bracket 3 minus square root 5x plus 1. That means that I've got two solutions, right? I've either got x is equal to 0, or I've got 3 minus the square root of 5x plus 1 is equal to 0. So that's square root 5x plus 1 is equal to 3. So 5x plus 1 is going to be equal to 9 because I square both sides. The 5x is equal to 8, so x is equal to 8 upon 5, which is the same thing as 1.6. Okay, so that should be our solution for the second part. Okay, so part 3, we now want to sketch the inverse function on the axis. Well, we're going to use the information that we've already learned. So first bit of information is that this coordinate here is 2.25. Okay. And the next bit of information is, well, we sketched on the graph of y equals x. So let's just try to do that. So that's y equals x, I think. And we found out that the x coordinate there, this thing, was 1.6. That's going to be 1.6. Okay. Oh, beg your pardon, 1.6. And this coordinate here is also going to be 1.6. And what do we know about inverse functions? Well, they're reflections in the line y equals x, right? So we're looking for a graph that's going to be a reflection in that red line. And we also know that the domain of the inverse function is going to be the same as the range of the original function. So in other words, we want a domain here of 2.25 or 0 to 2.25. And the range is going to be the same as the domain of the original function, which means that the uh, range of our inverse function is going to go from 0 to 3. So we kind of want a point that's going to end there. So our curve has got to go all the way up like that, like a reflection. Got to get this as nice as possible. It's got to go through there. It's kind of got to go up and be like that. Sorry that my curve isn't smooth. It's not so fantastic. It's not supposed to have like kinks in it. I'm sorry about that. But hopefully you get the idea. Really the key thing is it starts here, goes up, cuts through at the same point here, the intersection with the line y equals x, and it goes up to there. And this coordinate here should be 2.25, 3. Okay, so the next part of this particular functions question, what we've got is two functions g and h, which have got the following definitions. We want to find an expression for the inverse function. Well, the way we do the inverse function is basically we try to make x the subject. So here we've got y is equal to the cubed root of 8x cubed plus 3. So plus 3, beg your pardon. So we're going to cube both sides. So we're going to get y cubed is equal to 8x cubed plus 3. And so therefore 8x cubed is equal to y cubed minus 3. And so then we'll divide both sides by 8. So x cubed is equal to y cubed minus 3 all upon 8. And that means that x will be equal to the cubed root of y cubed minus 3 all upon 8. And the cube root of 8 is 2, so we can write this as a half. The cube root of y cubed minus 3. And so the last step really then is to say, what's the function here? It's called g, isn't it? We can then say g inverse x is equal to a half times by the cube root of x cubed minus 3, right? We just, in the last step, we replaced the y with an x. Okay, then carrying on with this functions question, we want to state the least value of the constant k such that the composite function g of h of x can be formed. Now, what does g of h of x really mean? It means that we take the function h of x, which is this, and we substitute it in to this function here, g. So in other words, this thing is going to become the x in this thing here. Now, what do we know? G of x requires that x must always be greater than 1. So what does that mean in this case? It means that e to the 4x, if it's going to be substituted into here, must always be greater than 1. So our condition is actually quite simple. It's that e to the power of 4x must always be greater than or equal to 1. And if that's the case, then what it means is that x must always be greater than or equal to 0, right? And so therefore our constant k, which represents the domain of h of x, right, must be 0, right? If that is the least value for which this thing can be formed. Okay, so k is equal to 0. Now notice it is 1 mark, right? So it's 1 mark, so actually the question should be quite straightforward in one sense, wouldn't require lots of working, but it does require you to understand what's happening with a composite function. I actually think that that is a little bit complicated and quite a few students will find it difficult. Okay, part 3 of this, we want to find and simplify an expression for g of h of x. So now we're actually going to form the composite function. So g is the cube root of 8x cubed plus 3, and we're going to substitute e to the 4x into there. So that's going to be the g of h of x, going to be the cube root of 8x cubed, so it's going to be 8e to the 4x cubed. What was it? Plus 3. Okay. And so therefore what we get is we get the cube root of 8e to the 12x, right? Because we multiply out the powers plus 3. And I think that's probably the simplest expression that we are able to get. All right, then we're in question 9, which is a circular measure question. All right, the area of a sector of a circle of radius 24 is 432 centimeters squared. Find the length of the arc of the sector. Well, it's probably helpful if we draw out a sector, right? It doesn't have to be accurate. Here's a sector like that. Sorry about that. This is the angle theta. This is the radius. This is the arc length S. Now, what are the formulas that we really need to know? The arc length is equal to r times pi theta. And the area is equal to a half r squared theta. This only works if we're using radians, of course. So if we're told the area of a sector is a sector of a circle of radius 24 is 432, we can just substitute that into our area formula. So we can say 432 is equal to a half times by 24 squared times by theta. So we can simplify this. So we've got 24 squared is 576 divided by 2 is equal to 288. And so theta will be equal to 432 divided by 288, which is 1.5 or 3 upon 2. Okay. How then are we going to find the length of the arc of the sector? Well, S is equal to r theta. Our radius is 24. Our arc length is now 3 upon 2. So if we multiply that out, that's going to give us 36. Okay, so 36 centimeters is the length of the arc of our sector. Okay, so here we are in part B of this question. We've got an isosceles triangle where this length is the same as this length, which is equal to y. Got a height of AD, and what we want to do is we want to find an expression for OB in terms of y and alpha. Well, it's only worth 1 mark, so it should be quite straightforward. And what I recommend that we do is we use the right angle triangle here, right? So this angle here is alpha, remember, because it's an isosceles triangle. Let's try to find this length here, BD, first. So cosine of alpha would be equal to adjacent, which is BD, over hypotenuse, which is y. We can rearrange that to get BD is equal to y cosine alpha. And if that's the case, well, OB is double that, so therefore we can say OB is 2 lots of BD, so it's 2y cos alpha, right? So that's our answer there. It's nice and straightforward. Okay then. Hence, we want to show that the area of the shaded region can be written as this thing here. Well, how are we going to find the area of the shaded region? We want to find the area of the triangle, right? This whole thing here, minus the area of the sector. Well, how are we going to find the area of the triangle? Well, we can just use half base times height. I think it's going to be the easiest thing. So our base here, we've already calculated, is the 2y cos alpha. And our height here we can find using trigonometry. So why don't we do that? So we can now say that, I'll do it up here, sine alpha is equal to opposite, which is AD, over hypotenuse, which is y. We rearrange that, we get y is equal to, beg your pardon, we get AD is equal to y sine alpha. Okay, so now I want to find the area of the triangle. The area of the triangle is equal to half the base, which is the length OB, so that's 2y cosine alpha, times by the height, which we just said was y sine alpha. We got y sine alpha, and the half and the 2 there are going to cancel off. Chop, chop. Oh, sorry, chop, chop, beg your pardon. And so we're going to get y squared cos alpha sine alpha. So here we get y squared cos alpha times by sine alpha. Okay, so that's the area of the triangle. How are we going to get the area of the shaded region? We need to subtract off the area of this sector here. Now, the area of a sector, is going to be equal to a half r squared theta. Now, what's our radius? Our radius is the same thing as this length here, which is the same as the length of BD, which we calculated earlier, is y cosine alpha. So we're going to have a half times by y cosine alpha squared times by alpha, okay, which is a half y squared cos squared alpha times by alpha, okay? Sorry, that's a bit messy there. Just trying to make sure you all can see the image. So then, the area shaded, now that thing is going to be equal to the area of the triangle, which was y squared cos alpha sine alpha minus the area of our sector, which was a half y squared alpha cos squared alpha. So a half y squared alpha cos squared alpha. Let me just double check, make sure I got that right. Yeah, it looks right to me. Okay, then. So now we're going to factorize out the common factors. Well, the common factor is y squared and cosine alpha. And we'll factorize out the half as well. So if we do that, what we're going to get is we're going to get a half y squared cosine alpha bracket 2 sine alpha, because remember we're factorizing out a half, right? So we're dividing by a half is the same as times by 2, minus alpha cosine alpha, right? Because cos squared divided by cos is cos. And there we go. That's our final answer to part 2 there. Okay, so we're in a binomial expansion style question now with question 10. We're told that in the expansion of ax plus b upon x squared to the power of 9, independent of x, that means there's no x there, is this number here, and the coefficient of x to the power of 6 is this number here. We want to show that a squared times by b is equal to negative 12. We want to find the value of a and the value of b. Right. It's going to be very, very tedious to expand this whole thing because it's going to have 10 terms. So what we want to do is we want to think a little bit more intelligently about this. We want to consider what each of those terms is going to look like. It's going to look something like this. So if we get ax plus b upon x squared all to the power of 9, then each single term is going to look like this. We're going to have ax to some power. We're going to have b upon x squared to some other power. And we're going to have a coefficient, which is going to be 9c something. Now, essentially what we've got to do is we've got to understand how these two powers work and this term here works. Now, these two powers must add up to give 9. Okay, so we can have 0 and 9, or 1 and 8, or 2 and 7, or 3 and 6, and so forth, right? They must add up to give 9. Now, a way you could think about that is you could say this power here is r, and then this power here would have to be 9 minus r. Okay? And as for this term here in the coefficient term, it can either be r or 9 minus r, because in the end it's going to give you the same thing. So we might as well just write here r. It doesn't actually matter which of those two values you choose. Now then, we've got two particular situations that we need to consider. One is we've got the term independent of x, so independent of x. And what that really means is we're going to get an x to the power of 0. And we've got another situation where we're going to get an x to the power of 6 term. Okay. Now, we've really got to think about how we can choose the powers that go here in such a way that we either get no x's or x to the power of 6. So let's just have a quick think about that. If I was to choose here r to be equal to 6, and this thing here to be equal to 3, then I'm going to get an x to the power of 6 divided by x to the power of 6. So my x's are all going to cancel off, and I'm going to be left with a term with no x's. Let me try to demonstrate that a little bit more carefully. So I'm going to write 9c6 ax to the power of 6 bracket b upon x squared to the power of 3. Please notice that when I do this, we're going to get an x to the 6th term here. An x squared cubed is also x to the 6. So these are going to cancel off. Okay. And then this thing here, I just copy that power. So let's try to expand all of that. So we've got 9c6. So I'm just going to use my calculator for that. 9c6 is 84. We've got 84 times by a to the power of 6, x to the power of 6, times by b cubed over x to the power of 6. And as I said, those things are going to cancel out. And so we're left with 84a to the power of 6, b to the power of 3. And we're told that that must be equal to this thing here, negative 145,152. So let's just write that out nice and carefully. So we're saying, therefore, 84 a to the power of 6, b to the power of 3 is equal to negative 145,152. I'm just going to see if I can divide that by 84. Right, so 145,152 divided by 84 gives me 1,728. So I think I'll just simplify this as a to the power of 6, b to the power of 3 is equal to negative 1728. Okay. Now then, we want to do the same thing, but now we want to get the term which is x to the power of 6. Go down. Okay. I want to get an x to the power of 6 term. How am I going to do that? Well, again, I just need to choose my terms carefully. So I'm going to get 9c something, ax to the power of something, b upon x squared to the power of something. And I want to choose this in such a way that everything's going to cancel off to give me an x to the 6. And of course, these two powers here have got to add up to give 9. Okay, so how can I do that? Well, let's see. If I had here 8 and 1, that should cancel off to give me what I want. So I'm going to put 8, 1 there, and 8 here. Let's just check that, make sure we're right. So we're going to get 9c8, I think is 9. Just check it, 9c8. Yeah, 9 times by a to the power of 8, x to the power of 8 times by b to the power of 1 over x squared. Well, I can cancel off, can't I? I divide top and bottom by x squared. And so what I'm going to get there is I'm going to get x to the power of 6. Okay? So then, if I do that, I'm going to get 9a to the power of 8 times by b. Okay? Now, we learned from this that this should be equal to negative 6912. Negative 6912. I'm going to say negative 6912 is equal to 9a to the power of 8 times by b. And hopefully that should also be divisible by 9. So 6912 divided by 9 is 768. So we get a to the power of 8b is equal to 768. So we've got these two things here. I'm going to label. I'm going to call that equation 1, I think. This thing here, equation 2. All right, then, what are we supposed to do? We want to show that a squared b is equal to negative 12. Well, I think I can take this thing here, equation 1, which is a to the 6, b to the power of 3. A to the 6, b to the power of 3, which is equal to negative 1728. And hopefully you can see that through the indices rule, if I was to write a squared b all to the power of 3, that's the same thing. And so I can cube root both sides. So I get a squared b. So I'm gonna cube root the 1728. So 1728 all to the power of a third. Okay. And so that's going to give me minus 12. So that's what I want. That's fantastic. Okay, well, if that's the case, then I can substitute this into 2. So I'm just going to rearrange. So I can say, therefore, b is going to be equal to minus 12 upon a squared. And I can substitute that into my a. So I'm going to get a to the power, into my equation 2, rather. So I'm going to get a to the power of 8 times my b, which is minus 12 upon a squared, is equal to 768. So 768. That means I'm going to get minus 12a to the power of 6 is equal to 768. So a to the power of 6 is 768. 768 divided through by 12. And that's 64. I think hopefully you should recognize that therefore A is going to be equal to 2. 2 to the power of 6 is 64. So if A is equal to 2, then B is going to equal to negative 12 over 2 squared. B is equal to negative 12 over 2 squared. 2 squared is 4, and 12 divided by 4 is 3. So B is equal to 3. So there we go. A is equal to 2, B is equal to 3, B is equal to negative 3 rather, and that should be the answer to your question. Okay, so here we are in question 11. We've got a line, x plus 3y equals k is tangent to the curve with this equation here. I want to find the value of k and hence the coordinates of the point where the line touches the curve. Right, now, what we're going to be doing is solving simultaneous equations, right? So we're going to solve these two equations simultaneously, and we're going to end up with a quadratic. Now then, because we're dealing here with a tangent to the curve, we're going to say that that quadratic is going to have one repeated solution. And when we have one repeated solution to our quadratic, that means the discriminant is equal to 0. So really this question is actually a discriminant question, and we need to understand the discriminant. B squared minus 4ac must be equal to 0 in this case. Okay? All right, then, how are we going to do this? Well, we're going to rearrange this equation here and substitute into the curve. And the easiest way to rearrange is to rearrange to get x. So x is equal to k minus 3y. And we're going to substitute into the curve. So substitute in the curve. Okay. All right, so if I do that, I'm going to get k minus 3y all squared plus y squared plus 2y minus 9 is equal to 0. So now what I've got to do is just got to expand that. So if I expand the bracket there, I'm going to get k squared minus 6ky plus 9y squared plus y squared plus 2y minus 9 is equal to 0. Right, let's collect our terms. We've got a 9y squared plus a y squared. So that's going to be equal to 10y squared. We've got a minus 6ky here and a plus 2y there. Well, we can factorize that out to get plus bracket 2 minus 6ky. And lastly, as our term without the y, the constant term, we've got a k squared minus 9. So hopefully what you can see here is we've got a quadratic. We've got a y squared, a y term, and a constant term. And just to clarify this for you, this thing here in our quadratic is a, right? So a is equal to 10. This thing here, that's our b. So b is 2 minus 6k. And this thing here is our c, right? So that's a, b, and c. And if I remind you what we said earlier, we want the discriminant of this quadratic to be equal to 0. So we want b squared minus 4ac to be equal to 0. Well, let's substitute in. We're going to get 2 minus 6k all squared minus 4 times by 10 times by k squared minus 9 be equal to 0. Let's expand that bracket. We're going to get 4 minus 24k plus 36k squared minus 40 k squared and minus 40 times by 9. That is going to be 360 plus 360. Okay, all equal to 0. All right, then, what we've got to do is we've got to simplify that. So we've got 36k squared minus 40k squared. That's negative 4k squared minus 24k. So that's just by itself. So we've got minus 24k. We've got 4 plus 360. Well, that is 364. Now, probably easier to divide our quadratic through by negative 4. So if we get that, we're going to get k squared plus 6k and then minus 91 is equal to 0. Okay, well, we've got a quadratic here. You could probably use your calculator. We could use the quadratic formula. I'm going to try to factorize it, I think. So we're going to get k and a k here. Now we're looking for two numbers that multiply together to give negative 91 and add up to give positive 6. So we're going to have one negative, one positive number. The positive number's got to be bigger. 91 is divisible by 7. So I think it'll be plus, let's see, plus 13 and minus 7, I think. So let's just try that out. 13 times by 7 is 91, and 13 plus minus 7 is 6. We've got two solutions here. We've either got k is equal to minus 13, or we've got k is equal to positive 7. Now, if we just remind ourselves of the question, up at the top, we were told that k is a positive constant. So immediately what we can do is we can eliminate this particular solution here. We're not interested in that. We just want k is equal to 7. Okay, so now let's go back up here. Here we had our quadratic from earlier. So we had 10y squared plus 2 minus 6ky plus k squared minus 9. So let's just repeat that. So 10y squared plus 6 minus 2k, no, 2 minus 6ky. And then plus k squared minus 9 is equal to 0. Okay, well then let's just simplify this by substituting in k is equal to 7. We get 10y squared plus 2 minus 6 times by 7 is 42. Plus k squared is 49, minus 9 is 40. We've got 10y squared minus 40y plus 40. Well, we can certainly divide that through by 10 to make our lives easier. So y squared minus 4y plus 4 is equal to 0. And that looks to me like that will factorize, give y minus 2 squared is equal to 0. Okay. Yeah, that looks right. And so if that's the case, then y is equal to 2. And by the way, we were expecting that, weren't we? Because we should get a repeated solution if this line is a tangent. We get y is equal to 2. Okay, if we got y is equal to 2, then how are we going to get our x coordinate? Well, we're going to substitute into here, right? X is equal to k minus 3y. So I'm going to write down x is equal to k minus 3y. And so k is 7 minus 3 times by 2. So 7 minus 6, which is equal to 1. So I think that should be the solution to our question. The coordinate is 2, 1, and k is equal to 6 up. Yeah, where the line touches the curve. Yeah, that looks right to me.